halogens: fluorine, chlorine, bromine, iodine, astatine. Fluorine atomic number 9, chlorine atomic number 17, bromine atomic number 35, iodine atomic number 53, astatine atomic number 85. And fluorine is yellow gas. And chlorine is greenish yellow gas. Bromine, red liquid, you can say brown red liquid. Iodine, violet solid. And astatine, radioactive element. Halogens are colored, and the color due to absorption of radiation in the visible region, which result in the excitation of outer electrons in the higher energy level. Absorption of radiation in visible region, which results in the excitation of outer electrons to higher energy level. And by absorbing different quanta of radiation, they display different colors. సో మెయిన్ ఇక్కడ రీజన్ ఏంటంటే, సపోజ్ X2 సిగ్మా బాండ్ ఫామ్ అయ్యేటప్పుడు అకార్డింగ్ టు MOT, X atomic orbital when they are combining and form two molecular orbitals, and X1 electron. So when they filled up, they occupy sigma pz. For fluorine 2pz, for chlorine 3pz, for bromine 4pz, like that. So it is a sigma pz and it is a sigma star pz. సో మనకి X2 సిగ్మా బాండ్ ఫామ్ అయ్యేటప్పుడు అకార్డింగ్ టు MOT, బాండింగ్ మాలిక్యులర్ ఆర్బిటాల్, యాంటీ బాండింగ్ మాలిక్యులర్ ఆర్బిటాల్. సో ఇలా మనకి 2 ఫామ్ అవుతాయి. అయితే ఇక్కడ మనకి ఈ ఎలక్ట్రాన్స్ అనేవి బాండింగ్ ఆర్బిటాల్ని ఆక్యుపై చేస్తాయి. ఎప్పుడైతే మనం దీని మీద లైట్ ఫోకస్ చేసామో ఈ ఎలక్ట్రాన్స్ ఎగ్జైట్ అవుతాయి. సో ఈ ఎలక్ట్రాన్స్ డీఎగ్జైట్ అయ్యేటప్పుడు బయటికి ఏదైతే రేడియేషన్ వస్తుందో, ఈ రేడియేషన్ అనేది మనకి విజిబుల్ రీజియన్లో ఉంటుంది. ఈ సిగ్మా బాండ్లో ఉన్న ఎలక్ట్రాన్స్ ఎగ్జైట్ అండ్ డీఎగ్జైట్ అవ్వటం వల్ల మనకి హాలోజన్స్ డిఫరెంట్ కలర్స్ షో చేస్తున్నాయి. అండ్ డిపెండ్స్ ఆన్ ది ఎనర్జీ గ్యాప్. సో వీటి మధ్య ఎనర్జీ గ్యాప్ అనేది డిఫరెంట్గా ఉంటుంది కాబట్టి డిఫరెంట్ ఫోటాన్స్ని అబ్జార్బ్ చేసుకుంటుంది అండ్ డిఫరెంట్ ఫోటాన్స్ని రిలీజ్ చేస్తుంది. అందుకే హాలోజన్స్కి డిఫరెంట్ కలర్స్ ఉన్నాయి. అటామిక్ ప్రాపర్టీస్: ionization enthalpy. So as we know that atomic radius top to bottom increases and ionization enthalpy decreases. Therefore fluorine, chlorine, bromine, iodine, no exception. Electronegativity: atomic radius increases, electronegativity also decreases. Therefore fluorine, chlorine, bromine, iodine. Fluorine most electronegative, iodine least electronegative. So there is no exception. Electron gain enthalpy: chlorine minus 349, fluorine minus 333, bromine minus 325, and iodine minus 296. So electron gain enthalpy including sign, it is the answer. That means chlorine has more attraction towards incoming electron. And if you compare electron affinity, chlorine greater than, fluorine greater than, bromine greater than iodine. సో ఎఫినిటీ అనేది క్లోరిన్కి ఎక్కువ ఉంటుంది, సైన్ పరంగా తీసుకుంటే క్లోరిన్కి లీస్ట్ అని తీసుకుంటాం, కానీ ఎలక్ట్రాన్ తీసుకునే కెపాసిటీ మాత్రం క్లోరిన్కి ఎక్కువ ఉంటుంది. హైడ్రేషన్ ఎంథాల్పీ ఎఫ్ మైనస్, Cl minus, Br minus, and I minus. When it is attracted with water, this is a strong H bonding, and when iodine attract with water, it is a weak H bonding. It is a weak H bonding. Therefore, strong force of attraction with water, more hydration enthalpy. More hydration enthalpy. F minus highest hydration enthalpy, I minus lowest hydration enthalpy. Electron gain enthalpy, chlorine more negative, fluorine less negative. Cl more negative, fluorine F less negative. And electron affinity, chlorine has more affinity. So the reason is, in the case of fluorine, electron added in the second orbit. Electron added in the second orbit. In the case of chlorine, electron added in the third orbit. Electron added in the third orbit. So ఇక్కడ మనకి ఏమవుతుందంటే, because of this small size, there is repulsion between these electrons, and because of this repulsion, fluorine has less negative value. Because of the repulsion, fluorine has less negative, and we can say because of the small size. But in the case of chlorine, it is a third orbit. It is a third orbit. So here, relative to fluorine, less repulsion. Relative to fluorine, less repulsion. Therefore, more negative value. Therefore, more negative value. So the reason we can say is, because of the small size, there is a repulsion between the electrons in the second orbit of fluorine after addition of electron. F2Cl2Br2I2 properties. Melting point, top to bottom increases. F2 less than Cl2 less than Br2 less than I2. There is no exception. And boiling point also, top to bottom increases. Top to bottom increases. There is no exception. And density also, top to bottom increases. Density also, top to bottom increases. And bond enthalpy, top to bottom decreases, because size of the atom increasing, bond enthalpy decreases. But bond enthalpy of F2 exception, it is exception. So the reason is, because of the small size, there is repulsion between the lone pairs. There is repulsion between the lone pairs. So because of this repulsion, F2 has low bond enthalpy than expected. Low bond enthalpy than expected. Because of the small size, there is repulsion between the lone pairs of fluorine. So there, because of the repulsion, it has low bond enthalpy than expected. Solubility of halogens in water. Solubility of halogens in water. F2 and Cl2 react with water. F2 and Cl2 react with water. Br2 and I2 sparingly soluble in water. Br2 and I2 sparingly soluble in water, but Br2 and I2 soluble in organic solvents. Soluble in organic solvents like chloroform, CCl4, CS2, hydrocarbons. Once they dissolve, once they dissolve, the solutions become, once they dissolve, the solutions become colored, because bromine and iodine having the color. So once they dissolve in the solvent, the solution also gets color. Oxidation states. So the lowest state is -1 for all halogens. For all halogens, -1, and of course 0 also possible. Next state is 0, and except fluorine, remaining 3 halogens, they also show +1, +3, plus 5 and plus 7. Other than 0 and minus 1, plus 1, plus 3, plus 5, plus 7 are also possible. And fluorine showing only minus and 0. So other oxidation states, other oxidation states not possible, not possible due to lack of d orbitals, due to lack of d orbitals. And it is most electronegative atom, most electronegative atom, therefore shows minus 1 state, therefore shows minus 1 state. And halogens chlorine, bromine, iodine showing the maximum oxidation states when they form oxides, when they form oxides and fluorides, when they form oxides and fluorides. Chlorine, bromine, iodine, so they are showing the higher oxidation states when they combine oxide, when they form oxides and fluorides. So in the oxides, oxygen, in the fluorides, fluorine, and these two atoms are small size atoms. These two atoms are small size atoms. And of course, chlorine and bromine also show plus 4 and plus 6, plus 4 and plus 6 in oxides, in oxides, and also in oxo acids, also in oxo acids. So chlorine and bromine also showing the plus 4 and plus 6 in oxides and oxo acids. Fluorine is present mainly as insoluble fluorides. Fluorine is present mainly as insoluble fluorides. Fluorspar, CaF2, cryolite, Na3Alf6, fluoroapatite, Ca3PO42, CaF2. సో టోటల్గా ఫార్ములా మనకి Ca9PO46, CaF2, apatite family. And small quantities are present in soil, river water plant, and bones and teeth of animals. Teeth of animals. Seawater contains chlorides, bromides, iodides of sodium, potassium, magnesium, and calcium. Seawater contain chloride, bromide, iodides of sodium, potassium, magnesium, and calcium, but mainly sodium chloride 2.5% by mass. Mainly sodium chloride 2.5% by mass. The deposits of the dried up seas, the deposits of the dried up seas. Dried up seas ante drying up of a body of water such as lake, river, or to the depletion of water or moisture from the something. సో మనకి వాటర్ ఇవాపరేట్ అయిపోయిన తర్వాత మిగిలిపోయే పార్ట్. సో మోస్ట్ ఆఫ్ ది కేసెస్ లెస్ అమౌంట్ ఆఫ్ వాటర్ ఉన్న ప్లేసెస్. సో ద డిపాజిట్స్ ఆఫ్ ది డ్రైడ్ అప్ సీస్ కంటైన్ దీస్ కాంపౌండ్స్, మెయిన్లీ సోడియం క్లోరైడ్ అండ్ కార్నలైట్. సోడియం క్లోరైడ్ అండ్ కార్నలైట్. సో కార్నలైట్ ఫార్ములా KCl MgCl2 6H2O. కార్నలైట్ ఫార్ములా KCl MgCl2 6H2O. Certain forms of marine life contains iodines in their systems. Certain forms of marine life contain iodine in their systems. That for example seawood. For example seawood. Seawood lo manaki example ante algae plant. For example algae plant. So ఇవి మెరైన్ లైఫ్ స్పేసెస్. సో వీటిలో మనకి 0.5% అయోడిన్ ఉంటుంది. సో వీటిలో మనకి 0.5% ఆ ప్లాంట్స్లో మనకి 0.5% అయోడిన్ ఉంటుంది. అండ్ చిలీ సాల్ట్ పీటర్లో కూడా మనకి 0.2% సోడియం అయోడేట్ ఉంటుంది. సోడియం అయోడేట్. చిలీ సాల్ట్ పీటర్లో కూడా మనకి 0.2% సోడియం అయోడేట్. సో దీస్ ఆర్ ది సోర్సెస్ ఆఫ్ క్లోరిన్, బ్రోమిన్, అయోడిన్. reduction potential F2 reduction potential value is more, I2 reduction potential value is less, and of course the value is decreasing. That means F2 can be easily reduced to F minus, and I2 cannot be easily converted to I minus. F2 అనేది మనకి F మైనస్గా ఈజీ కన్వర్ట్ అవుతుంది, అండ్ I2 ఈజీగా I మైనస్ కన్వర్ట్ కాదు. సో దట్ మీన్స్ F2కి రిడక్షన్ ఈజీగా అవుతుంది, అండ్ I మైనస్కి రిడక్షన్ రిలేటివ్లీ డిఫికల్ట్. రిడక్షన్ ఈజీ అంటే వీ కెన్ సే ఇట్ ఈస్ అ స్ట్రాంగ్ ఆక్సిడైజింగ్ ఏజెంట్. It is a strong oxidizing agent. So based on reduction potential values, we can say, so fluorine can be easily reduced. Therefore, fluorine is strong oxidizing agent in aqueous medium. So the decreasing ability of the halogens in solution down the group is evident from the standard electrode potential values. The oxidizing ability of the halogens in aqueous solution decreases down the group. సో మనకి రిడక్షన్ జరగాలంటే ఫస్ట్ X2 గ్యాస్ అనేది డిసోసియేట్ అయ్యి ఎక్స్ యాటమ్ ఫామ్ కావాలి, అండ్ ఎక్స్ యాటమ్ ఎలక్ట్రాన్ తీసుకొని ఎక్స్ మైనస్ కన్వర్ట్ కావాలి, అండ్ ఎక్స్ మైనస్ వాటర్లో ఉంది కాబట్టి హైడ్రేషన్ ఎంథాల్పీ. సో మనకి ఈ0 వాల్యూ అనేది బాండ్ ఎంథాల్పీ మీద డిపెండ్ అవుతుంది, ఎలక్ట్రాన్ గెయిన్ ఎంథాల్పీ మీద డిపెండ్ అవుతుంది, అండ్ హైడ్రేషన్ ఎంథాల్పీ మీద కూడా డిపెండ్ అవుతుంది. సో బేస్డ్ ఆన్ దీస్ 3 వాల్యూస్ ద electrode potential values are given. Chemical reactivity of halogens. All the halogens are highly reactive. And the reactivity of halogens decreases down the group. So previously we have discussed based on the electrode potential values. F2 is strong oxidizing agent, I2 is weak oxidizing agent. So the reason is the ready acceptance of electron is the reason for the strong oxidizing nature of halogens. F2 is the strongest oxidizing halogen, and it oxidizes other halides in solution or even in the solid phase also. F2 is a strongest oxidizing halogen, and it oxidizes other halide ions in solution or even in the solid phase also. In general, halogen oxidizes halide ions of higher atomic number. That means low atomic number halogen oxidizes high atomic number halide. For example, F2 plus Cl minus gives F minus plus Cl2. F2 plus Br minus gives F minus plus Br2. F2 plus I minus gives F minus plus I2. The reverse reaction is not possible. Low atomic number halogen oxidizes high atomic number halide. Low atomic number halogen oxidizes high atomic number halide. Similarly, Cl2 can oxidize Br minus. Cl2 can oxidize I minus. Cl is low atomic number and Br minus is high atomic number. Similarly, Br minus can oxidize Br2. Br2 can oxidize I minus to I2 plus Br minus. So Br2 low atomic number, I minus high atomic number. That means fluorine, chlorine, bromine, iodine. Fluorine can oxidize chlorine, bromine, iodine. Chlorine can oxidize bromine and iodine. Bromine can oxidize iodine. The reverse is not possible. సో మనకి టాప్‌లో ఉన్న ఎలిమెంటు బాటమ్‌లో ఉన్న ఎలిమెంట్ ఆక్సైడ్‌ని ఆక్సిడైజ్ చేస్తుంది. సో బాటమ్‌లో ఉన్న ఎలిమెంటు టాప్‌లో ఉన్న ఎలిమెంట్‌ని ఆక్సిడైజ్ చేయలేదు. Although chlorine has fluorine is less negative as compared to chlorine. Fకి Cl కంపేర్ చేస్తే Fకి మనకి లెస్ నెగెటివ్ వాల్యూ ఉంటుంది. క్లోరిన్‌కి మనకి మోర్ నెగెటివ్ వాల్యూ ఉంటుంది. ఎలక్ట్రాన్ గెయిన్ ఎంథాల్పీ. బట్ స్టిల్ ఫ్లోరిన్ ఈజ్ స్ట్రాంగర్ ఆక్సిడైజింగ్ ఏజెంట్. సో స్టేట్మెంట్ ఏంటంటే క్లోరిన్‌కి ఎలక్ట్రాన్ తీసుకున్నప్పుడు మోర్ ఎనర్జీ రిలీజ్ అవుతుంది. ఫ్లోరిన్‌కి ఎలక్ట్రాన్ తీసుకున్నప్పుడు లెస్ ఎనర్జీ రిలీజ్ అవుతుంది. సో దిస్ వాల్యూ ఈజ్ more negative value. It is more negative value. It is less negative value. But still, fluorine is fluorine is better oxidizing agent. Better oxidizing agent. So the reason is here F2 is dissociating to fluorine atom. Fluorine atom taking electron F minus attracting water and hydration. సో రిడక్షన్ పొటెన్షియల్ వాల్యూ అనేది ఒక ఎలక్ట్రాన్ గెయిన్ ఎంథాల్పీ మీద డిపెండ్ అవ్వదు. బాండ్ ఎంథాల్పీ మీద డిపెండ్ అవుతుంది. ఎలక్ట్రాన్ గెయిన్ ఎంథాల్పీ మీద డిపెండ్ అవుతుంది. అండ్ హైడ్రేషన్ ఎంథాల్పీ మీద కూడా డిపెండ్ అవుతుంది. సో ఈ 3 ఫ్యాక్టర్స్ కన్సిడర్ చేయాలి. సో ఇక్కడ మనకి మెయిన్‌గా ఎవరెవరు డామినేట్ చేస్తున్నారు అంటే ఈ 2 కేసెస్. సో ఇది ఎలాగో సపోర్ట్ చేయట్లేదు. సో దిస్ ఈజ్ నాట్ సపోర్టింగ్. సో ద ఓన్లీ సపోర్టింగ్ పాయింట్స్ ఆర్ దీస్ 2. If you compare bond enthalpy, Cl2 and F2, Cl2 bond enthalpy is more. That means F2 is easily breaking. F2 is easily breaking. So it is supporting. And next one is hydration enthalpy. Hydration enthalpy. If you compare F minus greater than Cl minus. అంటే F మైనస్కి హైడ్రేషన్ ఎంథాల్పీ ఎక్కువ. సో F మైనస్ వాటర్లో ఈజీగా ఫామ్ అవుతుందని అర్థం. సో హైడ్రేషన్ ఎంథాల్పీ సపోర్ట్ చేస్తుంది. బాండ్ ఎంథాల్పీ కూడా సపోర్ట్ చేస్తుంది. సపోర్ట్ చేయని పాయింట్ ఎవరు? ఎలక్ట్రాన్ గెయిన్ ఎంథాల్పీ సపోర్ట్ చేయట్లేదు. సో ద రీజన్ ఈస్ లో ఎంథాల్పీ ఆఫ్ డిసోసియేషన్ ఆఫ్ F2 and hydration enthalpy of F minus. Hydration enthalpy of F minus. Like in every group, in this group also, the second period element showing anomalous behavior. The second period elements showing anomalous behavior. The reason is its small size, highest electronegativity, low bond dissociation enthalpy, non-availability of d orbital in the valence shell. The valence shell. Small size, highest electronegativity, low F2 bond dissociation enthalpy, non-availability of d orbital in the valence shell. Some of the evidences are most of the reactions of fluorine are exothermic. Most of the reactions of fluorine are exothermic due to small and strong bond formed by its other elements. Due to small size and strong bond formed by its other elements. It forms only one oxo acid, but other halogens form number of oxo acids. Fluorine forms only one oxo acid, but other halogen forms many number of oxo acids. HF is liquid due to strong hydrogen bonding. HF is liquid due to strong hydrogen bonding. Other hydrogen halides HCl, HBr, HI, which have bigger size and less electronegativity are gases. Other hydrogen halides which have bigger size and less electronegativity are gases. That means HCl, HBr, HI are gases. Hydrogen bond is formed in HF due to small size and high electronegativity of fluorine. సో ఫ్లోరిన్లో మనకి హెచ్ బాండింగ్ తీసుకోవటానికి రీజన్ ఏంటంటే డ్యూ టు ఇట్స్ స్మాల్ సైజ్ అండ్ హై ఎలక్ట్రోనెగటివిటీ ఆఫ్ ఫ్లోరిన్. సో మనకి మెయిన్గా 3 ఎలిమెంట్స్ హెచ్ బాండింగ్లో ఇంపార్టెంట్. 3 ఎలిమెంట్స్. ఈ 3 ఎలిమెంట్స్ హెచ్ బాండింగ్లో షో చేయడానికి రీజన్ సో డ్యూ టు స్మాల్ సైజ్ అండ్ హై ఎలక్ట్రోనెగటివిటీ. ఈ 3 ఎలిమెంట్స్ హైడ్రోజన్ బాండింగ్లో పార్టిసిపేట్ చేయడానికి రీజన్ స్మాల్ సైజ్ అండ్ హై ఎలక్ట్రోనెగటివిటీ. Halogens reaction with water. F2 with water. F2 with water. When F2 react with water, F2 will be reduced and H2 will be oxidized. H2 will be oxidized. So here fluorine is reduced and H2O is oxidized. Therefore, fluorine oxidizes fluorine oxidizes water. Chlorine with water. Chlorine with water. When Cl2 react with water, it gives HCl plus HOCl, and HOCl is known as hypochlorous acid. Hypochlorous acid. And this reaction we can understand like this: Cl plus, Cl minus, H plus and OH minus. So HCl and HOCl. Br2 with water. Br2 with water. So when bromine react with water, the reaction similar to chlorine, therefore it produces HBr plus HOBr. HBr plus HOBr. HOBr is known as hypobromous acid. Hypobromous acid. I2 with water. I2 with water. So I2 with H2O, no reaction. I2 with H2O, no reaction. But I minus react with O2 in the presence of H plus produces I2 plus H2O. So in this case, I minus is oxidized and O2 is reduced. Hydrohalogen compounds HX. So H2 react with halogen and gives 2 moles of HX. So almost every halogen has affinity for hydrogen, and that affinity decreases. That means fluorine, chlorine, bromine, iodine. Fluorine has more affinity than iodine. Fluorine has more affinity than iodine. And almost all HX compounds are water soluble. All HX compounds are water soluble. So first property comparison, bond length. First property comparison, bond length. So HF less than HCl, HBr, HI. So HI bond is longer bond, HF bond is shorter bond. Next one is bond enthalpy. Bond enthalpy. HF bond is stronger and HBr bond is weak. So reason, hydrogen and fluorine, small size atoms, strong overlapping, effective overlapping. Hydrogen and iodine size difference is there, so bond strength is weak. Bond strength is weak. Next, acidic strength. Acidic strength. So low bond enthalpy, stronger the acid. Low bond enthalpy, stronger the acid. That means HI is strong acid, HF is weak acid. HI is strong acid, HF is weak acid. Now stability. Stability. HF is more stable than HCl, than HBr, than HI. The reason is this is a strong bond, therefore thermally stable, and it is a weak bond, therefore thermally unstable. Thermally unstable. Next one, melting point. Melting point. Melting point, HCl less than HBr, less than HF less than HI. So generally top to bottom melting point increases, but HF is exception because of hydrogen bonding. Because of hydrogen bonding, HF is exception. Boiling point, boiling point, HCl, HBr, HI, HF. Again here HF is exception because of the hydrogen bonding. So melting point ఏమో HF E ప్లస్ లో ఉంది, బాయిలింగ్ పాయింట్ ఏమో హైయెస్ట్ బాయిలింగ్ పాయింట్ HF. సో రీజన్ వీ హ్యావ్ టు సే హైడ్రోజన్ బాండింగ్. Hydrochloric acid. So hydrochloric acid is colorless, colorless, and it is having pungent smelling. Pungent means strong smell, very strong smell. So this HCl gas on liquefying, it converts into liquid, it converts into liquid, and the liquid form also colorless. Liquid form also colorless. On freezing, it forms white crystalline solid. On freezing, it forms white crystalline solid. And the boiling point of liquid is 189 Kelvin, and the freezing point of solid is 159 Kelvin. 159 Kelvin. And HCl gas, HCl in water, HCl in water, strong acid. HCl in water, strong acid. Now, how to prepare HCl? HCl preparation. We discuss about the laboratory preparation. We discuss about the laboratory preparation. In the laboratory preparation, we take sodium chloride and add concentrated sulfuric acid, and this solution heated up to 420 Kelvin, and it forms sodium bisulfate plus HCl. Sodium bisulfate plus HCl. And this sodium bisulfate, when treated with excess of NaCl, temperature about 823 Kelvin, it forms sodium sulfate and HCl. Sodium sulfate and HCl. Sodium chloride on treated with concentrated sulfuric acid at 420 Kelvin. Initially, it produces sodium bisulfate and hydrochloric gas. And this sodium bisulfate again treated with excess of sodium chloride about 823 Kelvin. It gives finally sodium sulfate, again HCl. And whatever the HCl is there, so this HCl can be dried. This HCl can be dried by using concentrated sulfuric acid. Concentrated sulfuric acid. Chemical properties. First one, when iron powder react with HCl, it gives FeCl2 plus H2. So here iron is oxidized and H plus is reduced. When iron react with HCl, we can also expect FeCl3 plus H2. But this reaction not possible. This reaction not possible because FeCl3 reacts with H2 and converts into FeCl2 plus HCl. FeCl2 plus HCl. Therefore, when we add HCl to the iron powder, initially it forms FeCl2 and further formation of FeCl3 not possible because of formation of H2. So H2 the formation of stops the formation of FeCl3. Stops the formation of FeCl3. HCl decomposes HCl decomposes salt of weaker acids. Salt of weaker acids. For example, Na2CO3. It is a salt of weak acid of H2CO3. H2CO3 weak acid ki salt idi. When sodium carbonate treated with HCl, so initially it forms NaCl plus H2CO3, and H2CO3 decomposes to H2O plus CO2. Similarly, sodium bicarbonate, it is a salt of H2CO3. When it is treated with HCl, it produces NaCl plus H2CO3, and H2CO3 decomposes to H2O plus CO2. H2O plus CO2. Next example, sodium sulfite. Sodium sulfite, when treated with HCl, it produces NaCl plus H2SO3, and H2SO3 decomposes to H2O plus SO2. H2O plus SO2. So like this, HCl decomposes salt of weaker acids. HCl decomposes salt of weaker acids. Aquaresia. So aquaresia is 3 parts of HCl and 1 part of conc HNO3. 3 parts of HCl, 1 part of HNO3. This mixture is aquaresia, and this mixture dissolves dissolves noble metals noble metals like gold and platinum. సో గోల్డ్ అండ్ ప్లాటినం డిజాల్వ్ చేయడానికి మనం ఈ యాక్వారీజా యూస్ చేయొచ్చు. ఫర్ ఎగ్జాంపుల్, గోల్డ్ రియాక్ట్స్ విత్ aquaresia and it produces AuCl4 minus. So gold is dissolved and converted into AuCl4 minus plus NO plus 2H2O plus 2H2O. Similarly, 3 moles of platinum reacts with 16 moles of H plus, 4 moles of NO3 minus, and 18 moles of Cl minus. So in this case, platinum is oxidized to PtCl6 minus 2. 3 moles of PtCl6 minus 2 plus 4 moles of NO gas and 8 moles of H2O. So in this case, the gold is oxidized to corresponding Au plus 3 state, and platinum is oxidized to corresponding plus 4 state. So both gold and platinum dissolved in aquaresia. It is aquaresia HCl and HNO3. HCl and HNO3. So these metals dissolve in aquaresia. HCl uses used in the manufacture of Cl2, ammonium chloride, glucose from stone starch. Used for extracting glue from bones and purifying the bone black, and used in medicine, and it is also laboratory reagent. It is also laboratory reagent. Chlorine. Chlorine is greenish yellow gas with pungent and suffocating smell. Chlorine is about 2 to 5 times heavier than air. Chlorine can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. Chlorine is soluble in water. Chlorine preparation. Laboratory preparation. Laboratory preparation. Hydrochloric acid, when heated with manganese dioxide, it gives manganese chloride plus chlorine plus water. So here chlorine is oxidized and manganese is reduced. Similarly, we can take sodium chloride in the presence of H2SO4 treated with KMnO4, and we know that KMnO4 is a strongly oxidizing agent. Therefore, KMnO4 will be converted to MnCl2, manganese reduced, plus Cl minus is oxidized to Cl2, and the remaining products are sodium bisulfate and H2O. sodium bisulfate and H2O. KMnO4, when treated with HCl directly, HCl is oxidized to Cl2 and KMnO4 reduced to MnCl2, MnCl2 plus KCl plus H2O. So here manganese is reduced and Cl minus is oxidized. Cl minus is oxidized. It is a laboratory preparation. Manufacturing, first one, decons process. Decons process. In the decons process, HCl treated with air, that means with O2, temperature 723 Kelvin, temperature 723 Kelvin, catalyst CuCl2, catalyst CuCl2. So HCl is oxidized to Cl2 and O2 is reduced to H2O. HCl is oxidized to Cl2 and O2 is reduced to O2, H2O. So it is a decons process. Second one, electrolysis of electrolysis of brine solution. Brine solution, that is NaCl solution. Brine solution means NaCl solution. So we take the solution in between two electrodes, so here we are having Na plus, Cl minus, H plus and OH minus. Suppose it is cathode and it is anode, and at anode Cl minus will be converted to Cl2. 2Cl minus gives Cl2 plus 2 electrons. Therefore at anode we get Cl2 gas in the form of bubbles, and at cathodes 2H plus 2 electrons gives H2. At cathode H2 gas will be released, at anode Cl2 gas will be released. Chemical properties of Cl2. First one, reaction with metals. Reaction with metals. Example, aluminium plus Cl2 gives AlCl3. Sodium plus Cl2 gives rise to sodium chloride. Iron plus Cl2 gives rise to FeCl3. Reaction with nonmetals. Phosphorus react with 6 moles of Cl2 gives rise to 4 moles of PCl3. 4 moles of PCl3. Sulfur react with 4 moles of Cl2 gives rise to 4 moles of S2Cl2. Sulfur, sulfur, chlorine, chlorine, S2Cl2. Iodine reacts with chlorine in water, produces iodic acid HiO3, and chlorine will be reduced to HCl. Chlorine will be reduced to HCl. So iodine is oxidized and chlorine is reduced. Reaction with SO2 water. SO2 water is reducing agent. SO2 water is reducing agent. Therefore, Cl2 will be reduced to HCl and SO2 will be oxidized to H2SO4. Similarly here Na2SO3 plus water, from this we can think H2SO3. H2SO3 means H2O plus SO2. So this combination also reducing agent combination. Therefore, Cl2 will be reduced to HCl and sodium sulfite will be oxidized to sodium sulfate. Sodium sulfate. Reaction with ferrous sulfate in acidic medium. Ferrous sulfate, ferrous sulfate reacts with Cl2 in the presence of acidic medium. Ferrous sulfate will be converted to ferric sulfate. Ferrous sulfate will be converted to ferric sulfate, and Cl2 will be converted to HCl. So here Fe plus 2 converted to Fe plus 3 oxidation. Cl2 will be reduced to HCl reduction. Reaction with ammonia. Reaction with ammonia. If ammonia excess, so 8 moles of ammonia reacts with 3 moles of Cl2 gives rise to 6 moles of ammonium chloride and N2 gas. Ammonium chloride and N2 gas. So here nitrogen is oxidized and chlorine is reduced. Chlorine is reduced. Suppose if ammonia treated with excess of Cl2, it produces NCl3 plus HCl. NCl3 plus HCl. So here chlorine is reduced, nitrogen is oxidized. Here chlorine is reduced, nitrogen is oxidized. And NCl3, it is a structure of NCl3. It is a structure of NCl3. When NCl3 treated with water, NCl3 treated with water, so ammonia lone pair attack on the chlorine vacant orbital. This bond will break. Ammonia attack on the chlorine vacant orbital. This bond will break. And ammonia H2O attack on the, not ammonia, H2O. H2O attack on the chlorine. H2O attack on the chlorine. H2O attack on the chlorine. This bond will break. Therefore, it produces HOCl plus NH3. HOCl plus NH3. అంటే మనం ఇక్కడ సింపుల్గా NCl బాండ్కి హైడ్రాలసిస్ చేసాం. ఇక్కడ OH గ్రూప్ యాడ్ అయింది, ఇక్కడ H గ్రూప్ యాడ్ అయింది. సో ఫైనల్లీ వీఆర్ గెటింగ్ 3 moles of HOCl and ammonia. Reaction with NaOH. Cold and dilute NaOH. When chlorine treated with cold and dilute NaOH, it produces NaCl plus NaOCl plus H2O. Similarly, when Br2 react with NaOH, it produces NaBr plus NaOBr plus H2O. Similarly, when treated I2 with NaOH, it gives NaI plus NaOI plus H2O. When chlorine treated with hot and concentrated NaOH, it gives NaCl plus NaClO3 plus H2O. NaCl plus NaClO3 plus H2O. Similarly, when bromine react with NaOH, it gives NaBr plus NaBrO3 plus H2O. Similarly, when I2 react with NaOH, it gives NaI plus NaIO3 plus H2O. NaI plus NaIO3 plus H2O. Reaction with dry slaked lime. So the formula of dry slaked lime is CaOH2, calcium hydroxide. So calcium hydroxide, when treated with chlorine, it gives CaCl2 plus CaOCl2 plus H2O. CaCl2 plus H2O. And composition of bleaching powder is bleaching powder composition CaOCl2, CaCl2, CaOH2 dot 2H2O. CaOCl2, CaCl2, CaOH2 dot 2H2O. It is a bleaching powder composition. Chlorine affinity for hydrogen. H2 react with Cl2 gives HCl. H2S react with Cl2 gives HCl plus sulfur. C10H16 react with Cl2, excess of Cl2 produces HCl plus carbon. HCl plus carbon. So these reactions indicates chlorine has a strong affinity for hydrogen. Bleaching action of chlorine water. Bleaching action of chlorine water. Chlorine water, that means moist Cl2. Chlorine water, that means moist Cl2, bleaches vegetables and organic materials. Bleaches vegetables and organic materials. So bleaching action of Cl2 plus water, bleaching action of chlorine water, permanent. Permanent. So when chlorine present in water, it gives two compounds HCl plus HOCl. HCl plus HOCl. And this HOCl decomposes and gives HCl plus nascent oxygen. HCl plus nascent oxygen. And this nascent oxygen, if we take any colored substance, when it is treated with chlorine water, and this nascent oxygen decolorizes the colored compound. Decolorizes the colored compound. That means it produces colorless substance. It produces colorless substance. Chlorine water gives HCl plus HOCl, hypochlorous acid, and hypochlorous acid decomposes to HCl plus nascent oxygen, and this nascent oxygen decolorizes the colored compounds, and this effect is permanent. This effect is permanent. That means once decolorized, again color formation not possible. Uses of Cl2 for bleaching wood pulp, bleaching cotton, bleaching textiles. Bleaching wood pulp, bleaching cotton, and bleaching textiles. For the extraction of gold and platinum. For the extraction of gold and platinum. In the manufacture of dyes, drugs, and organic compounds like carbon tetrachloride CCl4, chloroform CHCl3, refrigerants, and DDT. So DDT means it is a ethane molecule and three chlorine atoms CH and corresponding benzene para position chloro, corresponding benzene para position chloro. So it is a DDT. So DDT means dichloro diphenyl, dichloro diphenyl trichloro trichloroethane, trichloroethane. It is a full form of DDT. So dichloro diphenyl trichloroethane, trichloroethane. And chlorine next use is sterilizing drinking water. So drinking water ని స్టెరిలైజ్ చేయడం కోసం కూడా మనం క్లోరిన్ యూస్ చేస్తాం. అండ్ ప్రిపరేషన్ ఆఫ్ పాయిజనస్ గ్యాసెస్. ప్రిపరేషన్ ఆఫ్ పాయిజనస్ గ్యాసెస్. ఫస్ట్ వన్ పాస్జీన్ COCl2. First one is parsine COCl2. Next one is tear gas and also known as chloropicrin CCl3NO2. CCl3NO2 chloropicrin. And next one is mustard gas. Next one is mustard gas. Mustard gas CH2 double bond CH2 when treated with SCl2. ఈథీని SClతో ట్రీట్ చేసినప్పుడు సో మనకి కరస్పాండింగ్ మస్టర్డ్ గ్యాస్ వస్తుంది. Cl CH2 CH2 సల్ఫర్ CH2 CH2 Cl. Cl, this is a alkene type. So from ethylene you are getting CH2 CH2 sulfur and alkene type. So through electrophilic addition ఇది ఫామ్ అవుతుంది. Through electrophilic addition ఇది ఫామ్ అవుద్ది. సో సింపుల్గా Cl CH2 CH2 sulfur CH2 CH2 Cl. So preparation of poisonous gases, parsine COCl2, tear gas or chloropicrin, and mustard gas. These are the uses of chlorine. Oxo acids of halogen. Oxo acids of halogen. Fluorine forms only one oxo acid due to small size and high electronegativity. Fluorine forms only one oxo acid due to small size and high electronegativity. Chlorine, bromine, iodine form several oxo acids. Chlorine, bromine, iodine form several oxo acids. Most of them cannot be isolated in the pure state. Most of the oxo acids cannot be isolated in the pure state. They are stable only in aqueous medium or in the form of their salt. They are stable only in aqueous medium or in the form of their salt. And examples of oxo acids. First one, hypohalous acid. Hypohalous acid, also known as halic 1 acid. Halic 1 acid. For example, hypofluorous acid, hypochlorous acid, hypobromous acid, hypoiodous acid. Hypoiodous acid. Next one, halous acid. Halous acid, and also known as halic 2 acid. Halic 2 acid. In this category, we are having only one example, chlorous acid. Chlorous acid. And structure of chlorous acid is like this. Two lone pairs. Next category is halic acid. Next category is halic acid. And another name is halic 3 acid. Halic 3 acid. In this category, we are having HClO3, chloric acid, HBrO3, bromic acid, HiO3, iodic acid. And the structure for all these halic acids is, for example, chlorine we are writing, it is the structure of chloric acid. Like that we can write bromic acid and iodic acid. And next one is perhalic acid. Perhalic acid. Perhalic acid, and also known as halic 4 acid. Halic 4 acid. For example, perchloric acid HClO4, perbromic acid HBrO4, periodic acid HiO4. And the structure is chlorine OH group, double bond O, double bond O, double bond O. So it is a structure of perchloric acid. Like that we can also write perbromic acid and periodic acid. So all these acids are monoprotic acids. All these acids are monoprotic acids, or you can say monobasic acids. All these acids are monobasic acids. Interhalogen compounds, different halogens connected through covalent bond. Different type of halogens connected through covalent bond. For example, ClF, BrF, IF in case of fluorides. Next one is BrCl, ICl. Next one is IBr. So these are X dash type of molecules. Next one is ClF3, BrF3, IF3. Next one is ICl3. So these are X dash 3 type. Next one, ClF5, BrF5, IF5. IF5. So these are X dash 5 type. And last one, IF7. X X-7 type. And their physical state also important. So CLF is colorless gas, colorless gas. BRF pale brown, pale brown gas. And IF, it is unstable but detected spectroscopically. It is unstable but detected spectroscopically. That means very short period it is observed. And BRCL is gas. BRCL is gas. And of course, pure solid at room temperature also observed. Pure solid at room temperature is also observed. And ICL, two possibilities are there. First possibility, ruby red solid. Ruby red solid. It is alpha form. Alpha form. Next one is brown red solid. Brown red solid. It is known as beta form. It is beta form. And IBR black solid. IBR black solid. CLF3 colorless gas. CLF3 colorless gas. BRF3 yellow green liquid. Yellow green liquid. IF3 yellow powder. IF3 yellow powder. And ICL3 orange solid. ICL3 orange solid. Next, CLF5 colorless liquid. Colorless liquid. BRF5 colorless liquid. Colorless liquid. And IF5 colorless gas. Colorless gas but solid below 77 Kelvin. Below 77 Kelvin, IF5 is a solid. And IF7 colorless gas. IF7 colorless gas. So these are the physical states of interhalogen compounds. ICL3 exists as dimer I2Cl6. ICL3 exists as dimer I2Cl6. So iodine, chlorine, chlorine, chlorine. Iodine, chlorine, chlorine, chlorine. So these are the ICL3 molecules. Now here one chlorine lone pair, here another chlorine lone pair. So it will be donated to the iodine through the dative bond, and this lone pair donated to the iodine through the dative bond. Now this iodine has two more lone pairs. This iodine has two more lone pairs. So this iodine is sp3d2 hybridization, and this iodine also sp3d2. Therefore, we can write square planar for this iodine, and for this one also square planar. Therefore, overall molecule planar. Overall molecule planar. So it is a structure of I2Cl6. This is first lone pair, second lone pair, and this is first lone pair and second lone pair. So you can see octahedral parts here for octahedral parts, but two lone pairs are present. That's why square planar. So this is one square planar and this is another square planar. It is a structure of I2Cl6. Preparations of interhalogen compounds. So they can be prepared by the direct combination, by the direct combination, Otherwise, by the action of halogen on lower interhalogen compounds. By the action of halogen on the lower interhalogen compounds. For example, Cl2 plus F2, and we are taking equal volumes. This mixture is heated at 437 Kelvin. It gives mainly CLF compound. It gives mainly CLF compound. And Cl2 plus 3 moles of F2, 573 Kelvin, and we get corresponding ClF3 compound. So F2 here we are taking excess. That means the product depends on the reaction conditions. The product depends on the reaction conditions. Another example, Br2 plus F2 gives rise to 2BrF3, and here Br is diluted with water. Br2 diluted with water. In this case, we are getting BrF3. When Br2 treated with excess of F2, it gives BrF5. It gives BrF5. Next, I2 plus Cl2 gives ICl. I2 plus Cl2 gives ICl. And here we are taking the equimolar. Here we are taking the equimolar. I2 plus Cl2, 3 moles of Cl2 gives rise to 2 moles of ICl3, and Cl2 we are taking in excess. That means the product depends on the composition of halogens we are taking. So these are the some of the preparations of interhalogen compounds. Reactivity of interhalogens. Interhalogens are more reactive than halogens. Interhalogens are more reactive than halogens except F2. So reason is, in terms of bond enthalpy, X dash bond enthalpy, it is interhalogen. Interhalogen bond enthalpy less than halogen bond enthalpy. Therefore, interhalogen bond enthalpy bond is weak and halogen bond is strong. So weak bond dissociates in chemical reactions easily and they participate effectively in the reaction. Of course, we are having exception because F2 has low bond enthalpy because of the lone pair repulsions in the F2 molecules. Lone pair repulsions in the F2 molecules due to its small size. Due to its small size. So interhalogens are more reactive than halogens. Hydrolysis of interhalogen compounds. For example, if we take ClF, because of electronegative difference, partial positive, partial negative. When it is treated with water, so water partial positive, partial negative. Therefore, this bond we can break like this, and this bond we can break like this. So these two will combine and gives rise to HF, and these two will combine and gives rise to HOCl. So it is fluoride, hydrogen fluoride, and it is hypochlorous acid. Hypochlorous acid. And here if you see, fluorine is small in size and chlorine is bigger in size. Bigger in size. So smaller size anions forming the smaller size atoms forming the halides, like that means anionic related compounds, anionic related compounds, and bigger size atoms forms chlorous acid type of compounds. Suppose if I take X dash, it is we are considering bigger atom, and it is we are considering smaller atom. So when it is treated with water, smaller atom will be connected to hydrogen, bigger atom will be connected to OH group. Therefore, corresponding answer Hx dash plus HOX. Similarly, when we take X dash 3, X dash 3, when it is treated with water, in this case also, these three will be connected to hydrogen Hx dash, and the middle one connected to OH groups. Middle one connected to OH groups like this, and it loses water immediately and form corresponding XOH double bond O. So it is a halous acid. Halous acid. For example, chlorine, chlorous acid, bromine, bromous acid, iodine, iodous acid. For example, X dash 5. When it is treated with water, so in this case also, so we have to break this bond. X dash small atoms, these are small atoms, and small atoms will be connected to hydrogen, 5 moles of Hx dash, and the central atom, larger atom, will be connected to 5 OH groups, will be connected to 5 OH groups. Remove the H2O and remove the H2O, remove the H2O. So this can be written as X double bond O, double bond O, OH. So it is a halic acid, halic acid, chloric acid, bromic acid, iodic acid. Simply we can write HXO3. Simply we can write HXO3. Suppose XX dash 7 times. XX dash, X dash is 7 times. When it is treated with water, when it is treated with water, so water will break the corresponding interhalogen compound. Therefore, it forms 7 moles of HX dash and X connected to 7 water molecules, 7 hydroxy groups. Now remove the water, remove the 3 moles of water, and finally it gives X double bond O, double bond O, OH, double bond O. It is known as perhalic acid. Perhalic acid. Simply we can write HXO4. HXO4. Perchloric acid HClO4. Perbromic acid HBrO4. Periodic acid HiO4. So it is about the hydrolysis of interhalogen compounds. Interhalogens physical properties. Interhalogens are covalent and diamagnetic like halogens. Covalent and diamagnetic like halogens. And these are mostly solids and liquids at 298 Kelvin, that means room temperature. Volatile solids and liquids at 298 Kelvin except CLF, which is a gas. Except CLF, which is a gas. And physical properties, if you compare physical properties, the physical properties are in between the corresponding constituent halogens. For example, it is an interhalogen compound, and corresponding constituents are chlorine and fluorine. So the property is in between them, like solubility, refractive index, density. If you compare those, either this one or this one, so either increasing or decreasing, but it is in between them, it is in between. But for melting point and boiling point, melting point and boiling point, interhalogens always more melting point and boiling point than corresponding halogens. Corresponding halogens, that means CLF melting point is more than Cl2 and F2 melting point. ClF melting point is more than that of Cl2 and F2. Most of the physical properties are most of the physical properties of interhalogen compounds are between the corresponding constituents halogens. But for melting point and boiling point exception, interhalogens have more melting point boiling point than halogens. Uses of interhalogen compounds. They can be used as non-aqueous solvents. They can be used as non-aqueous solvents. And these are very powerful fluorinating agents. Very powerful fluorinating agents. For example, ClF3 and BrF3. ClF3 and BrF3 are used for the production of UF6 in the enrichment of uranium 235. ClF3 and BrF3 are used for the production of UF6 in the enrichment of uranium 235. For example, uranium react with ClF3. Uranium react with ClF3. It gives UF6 and ClF. Uranium react with ClF3 gives rise to UF6 and ClF. So in this way, uranium concentration can be increased and uranium can be removed from the ore.